On the next part of 6.5, we're going to look at how to solve trig equations involving multiple or compound angles. On the last example, okay, we just saw of just a single angle x, okay? Now, if we want to look at this solving the equation cosine 4x, this is a multiple angle, a quadruple, sorry, that wouldn't be quadruple. Yeah, it would be. A quadruple angle for x equals 1/2. Remember what this 4 does to the graph of cosine 4x. That's a period change. And so what we would see is that one period, we would go through one whole period for our cosine curve in between 0 and pi over 2 is actually how that would work. Because remember, to calculate period, it's 2 pi divided by the b value here. And so that would reduce to pi over 2. That's how I know we were going through a complete period from 0 to pi over 2. Now, if we look at where that new curve for cosine intersects our y equals 1/2, that's going to happen even more often, right? So that is visually what the solutions would look like. But how we're actually going to work this is, first off, we're going to go ahead and generate a list of angles that have a sine value of whatever it is we're looking for, okay? And then we are, from that, going to then, after we get our list of angles, then we'll get rid of the triple angle, okay? So it's important that you follow those steps. First of all, like we discussed on the last example, isolate the trig expression on one side. We can accomplish that by subtracting 5 from both sides. So now our equation looks like the sine of 3x equals a -1. Now, this is where you go ahead and you know, kind of on the last one, probably what we should have done is said, okay, what I'm going to do next is I'm going to take the inverse cosine of both sides. And so I will have x is going to be equal to all the angles that have a cosine value of -√2/2. Then we go ahead and break that apart into, you know, those two places where x is equal to, x has a cosine value of -√2/2. I think that would be a good idea because over here, the next thing I'm going to do is just isolate the 3x. I can accomplish that by taking the inverse sine of both sides. Okay? So now my equation looks like 3x equals the inverse sine of this number right here, -1. Now, once you have isolated the argument, which is the 3x, then you're going to say, well, what all angles have a sine value of -1? Now we're going to generate a list of those angles. Now, since this number right here was -1, and I know that that is a sine value of a quadrantal angle, we don't need to break it apart into the two different quadrants, because the only angle that has a sine value of -1 is 3 pi over 2, right? That's the angle, 270 degrees, that has a sine value of -1. Now, you're going to directly bring down this 3x, okay? Now, it's not just going to be 3 pi over 2. It's also going to be every single time that we hit down there at 3 pi over 2, okay? So, every angle that's also coterminal with 3 pi over 2 has a sine value of -1. Next, if you have a multiple angle, you're going to just solve for x. So we're going to divide everything through by 3 to solve for x. Y'all, dividing by 3 is the same thing as multiplying by a third, and I think I'll just divide that one by 3. So here's what our solutions for x will look like. Okay, here the 3's reduce, just leaving us with pi over 2 plus 2n pi over 3. Okay? So when they're asking for the solution set, it's just going to be the set of all x values such that x is equal to exactly what we have down there. It's going to be pi over 2 plus 2n pi over 3. Okay? Now, the next thing we need to do is part B, write the solution set, but just for answers that lie in between 0 and 2 pi. It could include 0, but not 2 pi. That's the bracket versus the parenthesis. Now, remember the way we do that. We let n be equal to 0, and then we'll let n be equal to 1, and then we'll let n be equal to 2, until we'll keep on going until we get past 2 pi. Okay? Now, when n is equal to 0, looking at our general solution, x is going to be pi over 2 plus 2 times 0 times pi is just going to be 0. So this is just x is equal to pi over 2. I'll kind of underline that. Okay? I'm going to write it in solution set form here in just a minute. Now, when n is equal to 1, our solutions are going to look like x is equal to pi over 2 plus 2 times 1 times pi, or just 2 pi over 3. Now, for this, we are going to need to add some fractions together. So to add fractions, we need a common denominator. To build up my denominator, I'm going to multiply by 3 over 3 there, and by 2 over 2 there. So that I have got 3 pi over 6 plus 4 pi over 6 is going to add together to give me 7 pi over 6. And we know where 7 pi over 6 is. It's down there in quadrant 3. That is in the interval between 0 and 2 pi. So there's another answer in my interval. 7 pi over 6. Underline it. Okay? Now, when n is equal to 2, okay, right back up here in my general solution set, when n is equal to 2, I'm going to be having the value of x is equal to pi over 2 plus 2 times 2 times pi, which is 4 pi over 3. Okay? So, again, build up your fractions to add your fractions together. 3 over 3 and 2 over 2. That gives us 3 pi over 6 plus 8 pi over 6. When we combine that together, that is 11 pi over 6. And 11 pi over 6 is about right in there. 11 pi over 6. Not quite to 2 pi. Okay? So there's a third solution in that interval. X is equal to 11 pi over 6. Okay? Now, if you keep going and let n be equal to 3, looking at our formula up here, remember, we're going to be getting a solution for x that is pi over 2 plus 2 times 3 times pi, which is 6 pi over 3. And if you take pi over 2 added to what would reduce to give us 2 pi, that's going to be bigger than 2 pi, bigger than what they wanted us to stop with up here, okay, in our interval. And so we don't have to go any more than that. These are our only 3 answers. So our solution set on that interval contains the values of pi over 2, 7 pi over 6, and 11 pi over 6. That's your answer for part B. Here's your answer for part A. Here's your answer for part B.